So we agree that it seems quite useful to know a bit more about the location of the epsilon-pseudospectrum. We said it many times before that the epsilon-pseudospectrum is in general larger than the epsilon neighborhood of the spectrum. And let's abbreviate this epsilon neighborhood of the spectrum as follows. As usual, we write ball with radius epsilon around, and here we usually give a point, and this time we give a set. And we mean this in the following sense. We take the union of all epsilon neighborhoods of points lambda in the spectrum. Just like we did in this numerical example here, where we were not only looking at the 50 little red stars, but instead at their epsilon neighborhoods and then the union of those. Okay. So we know the epsilon pseudospectrum is often larger than that neighborhood, but how much larger can it be? And the answer is given by our lemma 3. The epsilon pseudospectrum of A is always between this epsilon neighborhood of the spectrum and the ball with radius norm A plus epsilon around the origin. So we give an upper bound on the pseudospectrum here, and we will do one more thing. We will prove that equality holds here if A is a normal operator. Of course, in order to speak about normal operators, you need the adjoints. You have to switch to the Hilbert space context. But if you have that, then it turns out the epsilon pseudospectrum is just equal to the epsilon neighborhood of the spectrum. And of course, that means that all the information that's in the epsilon pseudospectrum is already contained in the spectrum. Which means that all these discussions about airplanes falling down is only interesting for non-normal operators. For normal operators, actually the spectrum also knows about mountains before time goes to infinity. And to be honest, many, but not all interesting systems are normal. And that's one of the explanations why not so many people speak about the pseudospectrum. Pretty much everyone believes that the spectrum is the ultimate answer, and it often is, in particular if your system is normal, if your operator behind the system is normal. So before we celebrate this lemma even more, we should probably give a proof. And let's start with a first computation that will turn out to prove the first inclusion. The pseudospectrum is characterized in terms of the norm of the inverse of A minus lambda I. And now let's try to transform this term until we see something about distance to the spectrum. And we know that we can switch from norm to spectral radius like this. And we know that this inequality is an equality if A is normal. In fact, it's the normality of the inverse of A minus lambda I that implies equality here. But one can show that this operator is normal if A is normal. So you should check back that this implication really holds. And then ask yourself or ask me in the problem session. So let's continue to work from here. So the spectral radius of that operator here is the maximum of the absolute values of the little gammas that are elements of the spectrum of this operator. But the spectral values of the inverse of an operator are just the inverses of the spectral values of the operator. So if you substitute gamma for 1 over delta, then while gamma is running around the spectrum of the inverse of A minus lambda I, delta is running around the spectrum of A minus lambda I, not inverted. Now instead of maximum 1 over modulus delta, you could just write 1 over minimum of modulus delta. And then of course the spectral values of A minus lambda identity are just the spectral values of A, and then you subtract lambda. So let's take a close look at this minimum down here. Okay, mu is running around the spectrum of A, so it's one of these blue points over here, maybe that one. And lambda is just a fixed point that is outside the spectrum, otherwise we couldn't talk about the inverse of A minus lambda I. And now you're computing the absolute value of the difference, which of course means it's the length of this line connecting lambda and mu, so it's the distance of these 2 points. And then of all these distances you're taking the minimum, which in this case is probably attained about when mu is here. And this is just what you would call the distance from the point lambda to the spectrum of A. So let's just replace this down here by distance lambda comma spec A. And I think this is just what we need to decide whether or not lambda is in the epsilon neighborhood of the spectrum of A, because if this distance is smaller than epsilon, we are closer than epsilon to the spectrum, so we are in this set, and otherwise we're not. Okay, let's label this inequality by 1. And now let's try to prove a second inequality that will help us to see this inclusion here. And we again start from the norm of the inverse of A minus lambda I. And then we transform this inverse here just like we did in the proof of lemma 1. So we first get the factor minus lambda out. Then because there's an inverse, it becomes minus 1 over lambda. And then use Neumann series for this inverse here. And then use triangle inequality here and submultiplicativity in this product here. And then finally geometric series here, where all the time we are assuming that the modulus of lambda is bigger than the norm of A, such that this number here is less than 1, and this operator here has norm less than 1, such that we can use Neumann series here and geometric series in what follows. And finally it just remains to multiply down here to get this result. If you look back, you will see pretty much the same computation in the proof of lemma 1.3, I think. Okay, let's also summarize this inequality and label it by 2. And I think then we are ready to conclude the inclusion of sets. That was our claim of lemma 3. Let's see how that goes. Okay, by inequality 1, we have that this property, distance of lambda to the spectrum of A less than epsilon, which is this denominator here, implies that the norm of the inverse of A minus lambda I is greater than 1 over epsilon. But then using inequality 2, if this norm is greater than 1 over epsilon, then this fraction is greater than 1 over epsilon, meaning that denominator modulus lambda minus norm A is less than epsilon. And now let's bring the norm A with a plus sign over to the other side. And let's see what we have got. This here means that lambda has distance less than epsilon to some point from the spectrum of A, so it must be in the epsilon neighborhood of the spectrum of A. This here means that lambda is in the epsilon-pseudospectrum of A. Well, and this last property here means that lambda is in a ball of radius norm A plus epsilon around 0. And together with these two implications, we just arrive at the conclusion that this set is contained in that set, and this set is contained in that set, as we claimed. In particular, we also showed that the first two sets are equal, so we have implication also in the other direction if A is a normal operator, because then we have equality in number 1. Good.